Hi, in this video, we're going to take a look at parameter tuning for supervised learning problems. Okay, so what I've done, I have a project that I need to make a prediction, maybe a regression target or a classification target. I've done my data, I've done my data collection, data aggregation, got it all together, did my data prep. I went through, a couple of different models to consider and landed on a final model that I'm going to use, maybe logistic regression, k-nearest neighbors, support vector machines, maybe stochastic gradient boosting, something like that. And now I want to get the best model I can for the model and data that I've got going. Okay, so something I want to say, and I'm going to say this multiple times, is that parameter tuning is actually the least important step along the way in all of our supervised learning project. Well, why is that? Well, first, the default settings on most implementations of supervised learning models are actually pretty good. So what we're trying to do when we talk about tuning is it's exactly that. I'm fine tuning the model. I'm not building it from the ground. I'm just trying to get a little bit better than what I already have. Also, the earlier a step is in the process, the more important it is. All right, so my design of experiments, my data collection, my aggregation of my data prep, and model selection are all more important. If I make a mistake on those steps, that mistake is going to propagate all the way through my process. Parameter tuning comes in relatively late. So also it's a late step, so it just doesn't have as much oomph as what would happen. Imagine that in my design of experiments, I'm going to go and decide what data I'm going to collect for my model. What if I completely, totally, and utterly miss an important predictor variable? Or maybe I go out and I collect only irrelevant predictor variables. Then my model is going to be junk. It's not going to be informative, not going to be useful. Parameter tuning, most things about the model have already been established by the time we get to this point. What we're trying to do, we're just trying to tweak things a little bit here and there to get things to be better. Now, this is different than like neural network parameter tuning. Neural networks, because they're so complicated, I'm focused on other types of modeling, more of like the spreadsheet problems, where I don't have to decide, how many hidden layers and how many nodes per layer there is. Here, we have like reasonable defaults settings, and we're taking something typically from scikit-learn and we're building a model. All right, so it's more important to get good quality predictor variables, have quality data so I don't have too much noise, missing values, outliers, etc. It's better to have good solid data prep and to choose a model structure that fits with my data very well. And so these are more important than the actual parameters I pick, because in scikit-learn and in most implementations of supervised learning, the default values are actually pretty good. All right, so why am I saying this? Because at some point, if you are working professionally, you're going to build a model and its accuracy isn't going to be good enough, and you're going to be crud. I've worked on this all the way up to this point, put on all this effort, and it's not good enough. So what are you going to do? What everybody else does, what I've done, what I do is that I'm going to try and parameter tune it to see if I can get like a magic bullet to carry it over. It's not going to. Just if your model is on default settings is grossly inadequate, parameter tuning is just going to make it less inadequate. So be mindful of that. If there's a huge difference from model performance from where it needs to be, you probably need to go back and consider getting new data fields to work with, or maybe consider different data prep, and try a few different model structures. And so here, simply tweaking parameters is not going to give you the necessary improvement that you want. But something that's nice about this step is that this is very automated. I can just write some code, hit the run button, and I can go walk away, go to lunch, and come back and I'll have the results. So overwhelmingly, we're going to do this, I'm going to make sure I get the best model I can. Even if default is pretty good, if I can get better, I want better, right? So we're definitely going to be doing parameter tuning no matter what, but just be mindful that it's the least important step on the whole process. All right, so here are some functions in scikit-learn. This is in the model selection part of scikit-learn. So here, first one I want to say is parameter grid and parameter sampler. These two functions, what these do, these identify what values, what combinations of parameter values to try. So parameter grid, I'm going to take some values for each parameter, let's say 3 each, and then for each parameter, I'm going to have the all possible combinations will be achieved. So imagine that I had, we had 3 parameters, and I put in 3 values each. Well, it's going to be 3 times 3 times 3, 27 different values that are going to be worked on. Well, if I had 4 parameters, 3 each, it'd be 3 times 3 times 3 times 3, 81 different parameter combinations. And so parameter grid, this does a good job of making sure I capture the full range, everything under consideration. It's naively, it's where you would start. If you had never thought about this, you would almost surely start with that parameter grid. Now, there's a disadvantage to this in that this parameter grid approach will set it up so that if there's a region of the parameter space, and think of it in higher dimensional mathematics, in the multi-dimensional state space of the parameters I could potentially pick, if there's a region that's very bad, not very useful, and parameter grid is going to keep on working on those over and over and over. So grid search, it's good for initial run, but it's not the one you're going to want to go with in the end. Now, parameter sampler, what it's going to do is that I assign probability distributions to each parameter, then it's going to go through and use random number generation to create the combination of parameters that are going to be considered. All right, now we've got grid search, where it's going to go through all the possible values that I give it. Then we have having grid search. So having grid search is grid search, but if it identifies a region in higher dimensional space that looks like it's not going to be very promising, it stops considering it to focus in only on the parameter values and parameter combinations that look like they're going to be fruitful. And so this can save us computation time by quite a bit. Now, there's also randomized search, cross-validation. So here, this is using that parameter sampler and using random number generation to pick what we're going to do. Also, there is a having random search cross-validation, which what this does, this says that random values, but also starts limiting things down to the area that looks promising in higher dimensional space. All right, so let's go ahead and run through an example. I'm going to use the California housing data set from scikit-learn, and I'm just going to use this fetch function to get it. I'm going to put everything into a data frame, and I always like to have everything nice and neat as one single data frame. That's my personal way of doing my programming. So I'm going to go ahead and have my data frame include the target variable. All right, so now what I'm going to do is I'm going to partition my data into train, validation, and test. Now here, the validation and test are not going to be that important because I'm going to end up using cross-validation, but potentially could have been. And here I'm just specifying what the predictors are. I'm setting up what my X and my Y are. Here is my training data for predictors, training data for target variable. And so now we can just see the data that I have. Now, if I was doing generalized linear models or support vector machines, something like that, I would go ahead and do some further, data prep like exponential transform, like Yo Johnson or Boxcox. But I'm using a tree model, so I'm just not going to worry about it. And I'm not going to center and scale or anything like that. So let's check out the histogram of the distributions. And a monotonic transformation on the data will not improve a tree model. I'm using random forest. That way I get to be lazy. So I'm not going to worry about the data prep. But the latitude and longitude, you can definitely see that these are interesting. There's probably 2 different regions on the map. Looking at that, maybe 4, maybe 3. All right, so now the types of parameter tuning that we could do, we can either do full range or halving. Full range does not consider the performance of the parameters up to that point. Halving considers the performance of the parameters up to that point and starts ignoring parameter regions that do not look promising. So this can improve our speed. Full range is better if I want to make sure that I got everything, I checked everything. Halving is better for computation speed. Also, we can have predetermined values or we can have random values. So in the full range or halving, full range, do not consider previous iterations and work to make sure that all corners of the parameter space are assessed. While the halving functions look at previous results and progressively reduce the parameter space to hone in on where are we going to get the best results. Typically what I start with a full range over a coarse grid, and when I get an idea of a good solid region, I start zooming in using halving. Now, we can also use predetermined values or random values. So functions that use predetermined values require the user to specify the exact values to try, while the random value functions, I just specify what is the distribution or possibly fixed finite, discrete, not finite, but discrete values to work with, and then it'll be sampled that way. All right, so now let's say I'm new to a function. I've never used a supervised learning model structure before. I don't know what to do. I'm not, I'm unaware. All right, so which parameters should I fine tune? You look at the help documentation, it can be a long list of parameters to consider. All right, well, generally speaking, if you don't know, go with the ones that are first in the help documentation. So the first parameters listed in the help documentation are usually the most important ones, not 100%. Different authors can do things, differently as much as they want, but this at least gives us a way to go if I have no clue whatsoever. Also, you can do an internet search, but this gives you a way of doing things if, like, let's say I don't have access to the internet while I'm working on my machine, like I have like high security on my data science projects. Now, how many parameters to tune will depend on my project and the amount of time I have, the amount of time I want to spend on parameter tuning. Now, what parameter values to try? All right, well, if it's discrete values, like you specify like auto, square root, half, or something like that, like a hard fixed character string for the parameter value, you just kind of have to try to figure that out depending on the model. But if I have numeric, what I have found as a good default starting point for parameter tuning is to take the default value, cut it in half, take the default value and double it, and then possibly have the original default value. That gives me 3 distinct values, and it's just something for me to like work with and progress with. If you are working in the care package in R, I know I'm talking about scikit-learn, but if you're working in the care package in R, the train function usually has pretty good default settings. And so if the help documentation doesn't look that great for you, try the train function in caret, and it usually does a pretty good job of making an initial guess of what you should try without looking at the data. Now, after I do my initial tuning, I'm going to look at the results and I'm going to say, hey, you know what? This value looks more promising than the others, and I'm going to zoom in the neighborhood of that particular parameter combination, and then I'm going to keep on zooming in to get the best result I can. If it ends up that a minimum or a maximum value was best, I'm going to expand my range to make sure that like if increasing the value substantially would improve the model, I don't want to miss that. And after I'm confident that I found the region of the best parameter combination, I'm going to focus in and keep tuning until I'm very confident in what I have. All right, I'm going to run through some examples, some things I need to say. These are not good parameter values I have in the model. On my machine, the data and the random forest was just taking too long for me to get the entire notebook done reasonably. So I have junk parameter values in here. I put them in here just so that it's fast. I picked values that would be quick, just so that you can see how is this process done. I wouldn't use these values at work, but I would go through this process. Now I'm going to do random forest regressor for this, and I'm just going to have the number of trees and the minimum samples in a leaf for my two parameters. And I'm just going to run with this. You'll notice that I don't have very many trees going on. 50 is half of the default. And then the minimum samples leaf, I think the default is 1. So this is much larger. This means that my trees will stop sooner in the splitting process. And so there aren't as many trees and they stop sooner. This is going to be faster to train than the default settings. All right, and so here, this is a parameter grid. So it's going to find all combinations of these 4 value, or these 2x2 values for us. Now, parameter sampler, what this is going to do, this is going to use random number generation from the distribution I give. If I give a list of values, so let's say that I did 50, 51, 52 as a list, then it's going to sample uniformly off of those 3 values. If I don't give a fixed list and instead give a random number generator, it's going to use that random number generator. And so this is a copy and paste of the help documentation, a generator on parameters sampled from given distributions, non-deterministic, iterable over random candidate combinations for hyperparameter search. If all parameters are presented as a list, sampling without replacement is performed. And then if at least one parameter is given a distribution, sampling with replacement is used. All right, so if I had all lists, it's going to do sampling without replacement. If I have one that is not a list, such as a random number generation, random integer, let's say, then it's going to do sampling with replacement for us. It is highly recommended to use continuous distributions for continuous parameters. And so here, I'm just saying I want 30 iterations, and it'll go through and just randomly generate combinations for me. Now, grid search for cross-validation. So those previous 2 functions go through and determine what parameter combinations to try. These functions actually go in and try them using cross-validation. I believe the default is 5-fold cross-validation. And so the grid search cross-validation is going to be exhaustive over all the parameter combinations that we can have. So there's several members for this. So when I use this function, I could use .fit, .predict. I also have a score method, score samples, predict, proba, and so on with this. The parameters of the estimator used to apply these methods are optimized by cross-validation grid search over a parameter grid. All right, so with this one, it's going to go over all possible combinations that I give it. And also I'm giving it fixed hard values. So this one is one where I determine the exact values of the parameters first. This is not with random number generation. And so I pass into the function, the estimator, the function I'm going to use, and a dictionary with the parameters of the model and the values I want to try. And so here it's going to take all possible combinations of these estimators with all possible combinations of this minimum samples in each leaf. And so I'm going to end up getting 4 different models off of this. Now, when I do this, I'm going to have the mean fit time, standard deviation of the fit time, mean score time, standard deviation of the score time. And so here, this helps me out figure out like how long is this going to take if I'm going to have to be doing this over and over and over. If it ends up that model performance is pretty close across a lot of them, but one of them is much faster, for the purpose of getting the job done, I'm going to go with a faster model. All right, so here we can see the parameter combinations off of these two columns. So it goes param, then name of the parameter, param, then name of the parameter. Here is the dictionary used for its individual row. And so now we're going to get our test scores. So here we have four different, so yeah, okay, this one, I guess it's four, no, it's five-fold cross-validation because there's 0, 1, 2, 3, 4. And so here's the average test score, standard deviation of the test score. So if we want to make sure that we can anticipate how the model will perform, the standard deviation of the test score is going to be more important to us. And then we get the ranking off of this. Now, having grid search cross-validation, this is going to search over the specified parameter values with successive halving. So it's going to narrow the range of considered parameter combinations so that it's not wasting iterations on things that probably don't look fruitful anyway. The search strategy starts evaluating all candidates with a small amount of resources and iteratively selects the best candidate using more and more resources. Oh, and hey, this one, I don't have the table for you. Oh, okay. But all right, so when this comes out, this will give me results similar to this, but here with only 4 combinations, I believe it's going to go through and just do the whole thing. If I had like a crazy number of combinations for my parameters, it's not going to hit all of them. Grid search, it will go through and hit all of them, and even if it looks like it's not going to be worth your time, it's going to go through grid, standard grid search is going to hit everything that you give it, which might be important if I need to be able to tell my stakeholders or my boss, like, yes, I was exhaustive on this. Yes, I'm very confident in my results. But if I have issues with computation time, I'm not going to want to do that. All right, so here in the halving process, you'll notice that it did 10, multiple times. It has, 50 and 51, we're not expecting a heck of a lot of a difference off of this. But so here it did more iterations than it did previously, but that's because I had such few parameter combinations. If I had a crazy number of parameter combinations to wade through, this would be a huge time savings. Now let's talk about the functions that use random number generation. And so let's talk about randomized search cross-validation. And so here, instead of using specified values, it's going to use random number generation, just like I talked about previously. If all parameters are presented as a list, it's going to do sampling without replacement. If at least one parameter is a distribution, it's going to be doing sampling with replacement. And so once again, we have a fit, score samples, predict proba, decision functions, transform, and inverse transform as our methods. The parameters of the estimator used to apply these methods are optimized by cross-validation search over parameter settings. In contrast to grid search cross-validation, not all parameters are tried out. Rather, a fixed number of parameter settings is sampled from the specific distributions. The number of parameter settings that are tried is given by the number of iterations. And once again, it is highly recommended to use continuous distributions or continuous parameters. All right, so we can take a look at this, and it's really the same game plan over and over and over. Now, there is a difference though. All right, so when I have the fixed values up front, I'm going to use a parameter grid. So my dictionary parameter itself is parameter grid. When I perform this, if I'm using random number generation, then it's going to be parameter distributions. And so there's a little bit of a difference. Going to really fit the same role. And so now it's going to use random number generation to go through and knock this out. And so I can see all the values. And so that's what 10 it did. And so we can see that number of estimators, 10 came up as the top and a bunch of different values. All right, so this is not, I wouldn't trust these results, by the way. For random forest, this is not what I would want to use to put in production. I did it this way to be fast for the purpose of creating this video. But just like with the other one, I've got information about how long it's going to take. so I can, if I need to, pick the model that's faster. I get a column of what parameter values are used, a dictionary of the parameter values. Then I get my cross-validation results to the far right, get the average of them and the standard deviation if I'm very concerned about wild swings from my model. Now, having random search cross-validation, this one is still in development. This is one that I don't think you should really trust it yet, and I'll show you why. The API and results of these estimators might change without any depreciation cycle. So notice that I had to pull in enable having search cross-validation to be able to execute this. Without this line of code, the function didn't work for me. So this is in development. Think of this as basically being a combination of random search and grid. Think of this as having with random values put together. And so as we work through, you can see that if I scroll through, there's a lot of pink on this. There's a lot of output and warnings. So I honestly wouldn't trust this. I would try another technique on this, but the final output is the same. And you can see that there are a lot more iterations on this one, even though I didn't give anything different than what was previous. Now, another way to go about parameter tuning is to do it manually. And in previous videos, I've done it manually using list comprehension. That's the way that I typically prefer to do it because I like to have everything like in a list, nice and compact, clean, I understand it. But that manual process by default doesn't give me the time of how long it takes, and it doesn't do the cross-validation for me. And so, there's advantages and disadvantages. Right. So big takeaways. First and foremost, parameter tuning is fine tuning. It will improve your model, but it's not going to take a horribly poor model and make it great. It's just not going to do that. Our data quality, the relationship between predictor variables and target variables, our model structure combined with our data is what is really going to be more important on our model, as long as we have reasonable default values. So when your model isn't good enough, don't look to parameter tuning to save you. If you're like me, you're still going to try it because it's easy. It doesn't take a lot of work. You start doing parameter tuning, hit the run button, go to lunch, come back, and you get disappointed that it didn't do as well as you had hoped. But when I've been in that position, I knew it was that way, but I would rather try a quick and easy thing to try and just let it run and then go back to what I knew I was going to have to do anyway. All right, well, that's all I've got for you. Life is short. Do math.